Here's what we'll cover in this video. Motorola engineers coined it in the 1980s to describe a manufacturing process so tight it produces only 3.4 defects per million opportunities. Decades later, that exact framework, borrowed wholesale math and all, is now how the best clinical laboratories quantify whether their testing is actually good enough to trust. Here's the uncomfortable translation. Most clinical laboratory testing, benchmarked against real EQA data, runs somewhere between 3 and 5 sigma, not 6. At 4 sigma, that's over 6,000 defects per million opportunities. At 3 sigma, it's over 66,000. The gap between where labs actually sit and where the framework's name implies isn't small. Precisely, sigma, in this context, is a single number expressing how many standard deviations of your total allowable error budget fit between your method's actual performance and the point of failure. Higher sigma means more room for error before a result becomes clinically wrong. A direct, quantitative measure of analytical quality, not a vague quality slogan. The formula pulls 3 numbers you should already have on hand: total allowable error, your method's bias, and its coefficient of variation. Subtract bias from T, divide by CV%, and the result is your sigma, expressed in the same standard deviation units as everything else in your QC program. The lineage is short but consequential. Motorola formalized 6 sigma in 1986. General Electric scaled it into a corporate standard through the 1990s. James Westgard adapted the exact math to clinical laboratory QC starting in the early 2000s, and it's his adaptation, not the original manufacturing version, that you'll actually use. Before Sigma metrics, QC design was largely one-size-fits-all, the same Westgard rule set, the same control frequency, applied to every analyte regardless of how good or bad that specific method actually was. Sigma changes the unit of analysis from "did this run pass" to "how much genuine safety margin does this method have?" A fundamentally different and far more honest question. Sigma isn't a lab-wide grade, it varies enormously analyte to analyte, and knowing why matters as much as knowing the number. T stringency, matrix susceptibility, and method maturity all move it independently. Published EQA-derived benchmarks show glucose commonly running 4 to 5 sigma, HbA1c closer to 3.5 to 4, and sodium, despite being one of the most basic tests in the lab, often sitting stubbornly below 3, purely because its allowable error window is so tight. Let's compute one with real numbers. Your glucose method has a T of 10%, a validated bias of 1.2%, and a CV of 2%. Subtract bias from T. 10 minus 1.2 is 8.8. Divide by CV. 8.8 divided by 2 is 4.4. Your sigma is 4.4, solidly in the good tier, comfortable with standard multi-rule QC. The resulting number maps onto 4 operational tiers, each demanding a genuinely different QC posture. 6 or above is world-class. A single rule with minimal controls suffices. 4 to 6 is good, standard multi-rule QC handles it. 3 to 4 is marginal, needing tighter rules and more frequent controls. Below 3, no QC strategy compensates, the method itself needs to change. The single most common way labs get this calculation quietly wrong: using the wrong T-source. CLIA acceptance limits, biological variation-derived goals, and manufacturer claims can differ by a factor of 2 or more for the same analyte, and plugging in the wrong one doesn't just shift your sigma slightly, it can flip your QC strategy entirely. A single sigma number, computed at one concentration level, can also mislead on its own. Compute it at your method's low, normal, and high decision-relevant concentrations separately, and it's common to see meaningfully different sigma values across the range. The same method behaving like a 5 sigma performer at normal concentrations and a 3 sigma performer near a critical cutoff. Sigma is also gameable unintentionally or otherwise. Cherry-picking a lenient T, computing bias from a single comparison point instead of a proper method comparison study, or excluding outlier CV data all inflate the number without improving actual performance, and a scatter of real replicate data honestly plotted is usually enough to catch it. Does a higher computed sigma actually translate into fewer real-world reporting errors? The published evidence, while not perfectly clean, says yes, labs with higher sigma-metric analytes consistently show lower rates of QC rejections, repeat testing, and delta check flags, which is exactly the kind of downstream signal you'd expect if the number means what it claims to. It's worth being precise about what sigma adds over CV% alone. CV% tells you how reproducible your method is. Full stop. Sigma tells you how much of your clinical error budget that reproducibility, combined with your bias, actually consumes, Two methods with identical CV% can have wildly different sigma if their T or bias differ. The through line for this chapter: sigma is only as trustworthy as the T, bias, and CV% you feed it. Compute it carefully at the concentrations that matter clinically, and treat a suspiciously high number with the same scrutiny as a low one. Quick pause. If this level of applied detail is useful for your quality program, subscribing keeps this series coming. This is the payoff of the whole framework. Sigma tells you exactly which Westgard rules and how much QC frequency a given method actually needs, instead of applying the same multi-rule set everywhere by default. World-class methods can run a single 1_3s rule with two controls as shift. Marginal methods need the full multi-rule set. 1_3s, 2_2s, or _4s, for _1s, run far more frequently, sometimes bracketing every batch. The visual tool built specifically for this is the OPSpecs chart, operating specifications, plotting bias on one axis against imprecision on the other, with diagonal boundary lines marking each sigma tier. A method's point falling in the upper right danger zone needs immediate attention regardless of what its individual bias or CV% looked like in isolation. Quick pause. If this breakdown is helping you, take a second to hit like and subscribe. It genuinely takes a lot of effort to make videos like this, and your support keeps them coming. Turned into a practical scheduling decision. A 6 sigma analyte might justify QC once per shift. A 4 sigma analyte needs QC bracketing every batch. A marginal 3 to 4 sigma analyte needs QC before and after every batch with tighter rejection criteria, the same lab, same day, running genuinely different QC intensity depending purely on each analyte's sigma. Ignore this and apply uniform QC everywhere, and the failure mode runs in both directions. High sigma methods get needlessly over-controlled, burning reagent and technologist time on runs that were never at real risk. Low sigma methods get under-controlled, with rejection criteria too loose to catch errors that genuinely matter clinically. Labs that have made this switch report the pattern consistently. Total QC events per month actually drop overall. Fewer wasted controls on high sigma analytes more than offsetting the added controls on marginal ones, while genuine error catch rates on the analytes that matter most measurably improve. The core design principle to carry forward: QC frequency and rule strictness should be a direct function of sigma, not a lab-wide default. Every analyte earns its own QC intensity based on its own margin. DPMO, defects per million opportunities, is Sigma's companion metric, and it's the one that actually resonates with hospital administration. Count your out-of-range QC events, delta check failures, and PT flags, divide by testing opportunities, multiply by 1,000,000. It converts abstract sigma into a number that reads exactly like a defect rate, because that's precisely what it is. Every point of DPMO reduction maps onto a real cost line item. Repeat testing from rejected runs, extended technologist hours chasing corrective action, and, at the extreme end, the liability exposure from a clinically consequential error all scale directly with how far a lab sits from its sigma target. Cost of poor quality frameworks routinely estimate this at several % of total lab operating budget for chronically low sigma programs. 6 sigma isn't just a metric, it's paired with DMAIC, a 5-phase improvement methodology built specifically to move that number, not just report it. Define the problem precisely. Measure current performance honestly. Analyze root cause statistically. Improve the process. Control the gain so it doesn't quietly erode back. Take a technical scenario, not a patient one. A chemistry section's high sensitivity troponin assay sits at sigma 3.2 marginal, below the 4 sigma minimum. Define. Reduce false critical delta check flags. Measure baseline sigma, current CV of 4.1%, bias of 2.8% against a T of 20%. That's the starting point for the improvement phases that follow. Analyze surfaces the actual driver. Statistical breakdown shows bias, not imprecision, dominating the error budget, traced to a calibrator verification interval that had quietly stretched from weekly to monthly understaffing pressure. The analyze phase exists precisely to stop teams from improving the wrong variable. Improve restored the weekly calibrator verification interval and added a documented sign-off step. Control locked it in with an automated LIS reminder, not a memory-dependent habit. 3 months later, the same formula, same T, tells a different story. Sigma climbs from 3.2 to 4.6, crossing fully into the good tier. The pattern worth internalizing. DMAIC's value isn't the acronym, it's the discipline of measuring before diagnosing and diagnosing before fixing. A Tropin and Sigma problem that looked like an imprecision issue turned out to be a calibration interval issue entirely. One more thing before we wrap. If your lab has a Sigma QC scenario worth breaking down, drop it in the comments. Getting started concretely. Pull T from a defensible documented source for every analyte. Compute Sigma at clinically relevant concentrations, not just the midpoint. Map each Sigma tier to a specific QC design, not a uniform default. Track DPMO monthly, not just at accreditation review. And target 4 Sigma or better as your floor, not your ceiling. 2 pitfalls undo most first attempts at this. Computing Sigma once and treating it as permanent, reagent lots, calibration, and instrument aging all shift it, so recompute quarterly at minimum. And copying another lab's Sigma benchmarks wholesale, your T-source, your platform, and your patient population all make your numbers genuinely yours, not transferable. One misconception worth retiring. A high Sigma metric does not mean QC can be safely relaxed or skipped. Even a genuine Six Sigma method still requires ongoing verification. Sigma tells you how much QC you need, never whether you need any at all. Six Sigma gives your lab a shared, quantitative language for a question every QC program is really trying to answer. How much safety margin does this result actually have? Compute it honestly, design QC from it deliberately, and revisit it as often as your methods actually change. Final recap. Sigma equals T minus bias, divided by CV%. Below 3 Sigma, QC alone can't fix a method, it needs to change. DPMO converts Sigma into a defect rate language administrators understand. DMAIC is the methodology that actually moves the number. And a high Sigma changes your QC design, it never eliminates the need for it. Here are the key references and sources for this video. Thanks so much for watching. If this helped, like the video and subscribe for more clear, simple explainers, and I'll see you in the next one.